Greetings. My name is Professor Duke Orata. We are continuing with our lectures dealing with steady flow and jet propulsion. Today we want to look at convergent divergent nozzles. Last time spoke about convergent nozzles, and I keep encouraging you once again and go through our earlier lectures systematically so that we are all together. So we want to look at convergent divergent nozzles. Divergent nozzles. So again, the schematic for this, just like in the case of convergent nozzles, we have try to draw it as best as we can. So this is our throat. At 1, because we're assuming that initial velocity is 0. Now, if we operate this convergent divergent nozzle at the appropriate design pressure ratio at the throat and exit areas, then we should have the flow from subsonic to supersonic velocity. So just know that if we operate at the appropriate design pressure ratio for throat and exit areas, then we'll have our flow from subsonic to supersonic velocity. Again, that's only when we operate at the design pressure ratio, those particular state points. Now, and in that particular case, the axial pressure and velocity profiles will be given as follows. Velocity profiles, let's see how they look like. So for our axial pressure, for the design let's call this A. Let's call that curve A. And of course, for the velocity, we'll have our mass flow and distance along the axis. So we'll have that A. So we'll keep drawing in on this particular diagram. Now, let's just again still keep in mind that convergent divergent nozzle. Let's have that picture in mind. Remember, that's P is the downstream pressure. You see that's throat pressure, state point 2, state point 1. So we continuously, but that's a convergent divergent nozzle. Now, when you open the valve and we lower P1, and we lower the pressure P1, as we open the valve and we lower the pressure P1, what kind of profile will we get, and what do we expect to happen? Remember, as we lower the pressure, there will be increase in velocity. So if we have that particular point, there will be increase in velocity, and then that diffusion. In other words, we will have the convergent duct acting like a subsonic nozzle and the divergent duct acting also like a subsonic nozzle, subsonic diffuser. We need some space here. Let's see. So let's say as we lower the pressure, if we lower P1, the convergent duct will act as a subsonic nozzle. It will act as a subsonic nozzle. While the divergent duct will act as a subsonic diffuser. Now, these terms which we are using, you need to remember from our earlier discussions, and that's why I keep encouraging you to go through our discussions systematically. We had said that dA over A, change in area, we said it was given by VdP 1 over C squared minus 1 over A squared, if you remember correctly. And remember, we related that to sound, and we have said that A squared was minus V squared del P del V and a constant entropy. This we discussed in our earlier lectures. And so what is the import of this? The import of this is that when the pressure, let me just delete a little bit of this. When the pressure is reduced, that's when you're dealing with a nozzle. Then in that particular case, when C is less than A, that you're talking of the subsonic mode. When C is less than A, that's when we have a convergence. And that is because dA is negative. Remember? Look at our earlier lectures. And in the case of a diffuser, when dP is greater than 0, when C is less than A, so that you're in the subsonic mode, then what does it mean? dA here is positive. And so when you have this in mind, that is what you transpose to interpret what we have talked about here, that the convergent duct acts as a subsonic nozzle and the divergent duct as a subsonic diffuser. So when you're talking about that, it means that this velocity is less than A, this velocity is less than A, that is the velocity, the actual fluid velocity is less than that of sound. We had called that, we had related that to sound. Remember that. Now, as we continue, so what is the profile? What is the profile at that particular point? At that particular point, what will be the profile? We have here, which let's call it B, curve B, given by curve B. And of course, in this particular case, so this is curve A, that will correspond to B. So I'm putting in these quantities simultaneously in these two diagrams. In these two diagrams. That's why I'm not erasing those particular diagrams. Now, we are going to continue having an increase in mass flow. The increase in mass flow rate, we're going to have that increase. It will continue until that point where the throat pressure is equal to the critical pressure. Remember, we have talked about CPR, the critical pressure ratio. So we are saying that the mass flow rate will increase until when the throat pressure equals the critical pressure. That is throat pressure. That is critical pressure. So at that point, the nozzle will be choked. There will be no change in the mass flow. There will be no change in the mass flow. So nozzle choked. We talked about that in the earlier lectures. So again, I keep encouraging you to go systematically through these lectures because we are building on them systematically. We are avoiding skipping anything, so we're just building them systematically. So if you follow them stepwise, then you should be able to follow these things quite easily. Now, suppose we continue lowering the pressure. Let us say we continue lowering the pressure. We continue lowering the pressure, the downstream pressure. We are continuing to lower it. Of course, what will happen? Remember, once the throat pressure is equal to the critical pressure, there will be no change. So we have the nozzle is really choked. But what will be the situation? Now, remember that when you continue lowering this pressure, it becomes now more difficult to have constancy of the three fundamental equations which deals with fluid dynamics in these ducts. That is the energy equation, the mass equation or continuity equation, and that of entropy. It's very important for us to note that. Let's just write that down. That is, as we continue lowering PE, the issue here will be that in the flow in this duct now, it will become a challenge in the case of flow of this duct to have those three fundamental equations acceptable or be solved simultaneously. Those three equations dealing with constancy. The constancy in energy, constancy in mass, and entropy. So the simultaneous solution of the three equations on constancy, that is dealing with mass, energy, and entropy, becomes a major challenge. So what does that mean? It means that the pressure profile will not necessarily be the same as we expected. Where we have the system choke, so we'll have that kind of a profile, and here also we will have kind of a profile, and it becomes even more erratic as we lower PE further. As we lower PE further, we get more erratic profiles, because it is very difficult for this to be fulfilled. That is mass being constant, energy being constant, and entropy being constant. Now, which one is the culprit here? The culprit here is the entropy. This is the culprit. So you can keep mass, energy, and continuity constant, but not the entropy. And why is that so? That is so because in the process, we can have the development of a shock wave. We talked about that in our earlier lectures. And what will be the impact or the import of having the shock wave? One, there will be increase in pressure. That's one. Number two, in addition to increase in pressure, there will be increase in entropy. And finally, there will be deceleration. There will be deceleration of the flow from supersonic to subsonic flow. Very important for us to note that. So what are we saying? there will be development of a shock wave. Very important for us to know that. And what will this shock wave do? There will be increase. There will be increase in pressure, increase in entropy, and deceleration from supersonic flow to subsonic flow. And this is understood. This is understood that you actually need a convergence duct for us to have isentropic diffusion. You'll have to have a convergent duct for us to have an isentropic diffusion. So the culprit in all this is the entropy. The culprit there is the entropy. And so definitely the profiles will now be different. They will not be the normal profiles, pressure and velocity profiles which we are used to in the case of isentropic diffusion. Now, as the flow continues, because this shock wave is just of a short distance, not that, just of a short distance. So it will quickly join the flow in the divergent duct. It will quickly join the flow in the divergent duct, and of course it will be dissipated there. And of course, like we had seen in the case of convergent nozzles, if you lower this pressure, the downstream pressure, if lowered further below the design pressure, then it's no longer a one-dimensional solution. It becomes quite a multiple solution and much more complex, just as we saw when we talked about the convergent nozzles. So we will stop at this particular point. We are still continuing.